two-body reassessment, and I chose problem 8.6 from Classical Mechanics by Taylor. And it says, show that in the center mass frame, the angular momentum of L1 of particle 1 is related to the total angular momentum L by L1 equals m2 L over m, and likewise L2 is equal to m1 L over m. Since L is conserved, this shows that the same is true of L1 and L2 separately in the center mass frame. So we want to show this and this, but we have to start with the total angular momentum. And we get this equation from the book, it's equation 8.9, and we have to solve for the regular R vector, regular R, and we get R1 and R in here, big R, and we have to take the derivative of it because we're going to need to plug back into this equation. So whenever we take the derivative of it, R1, we just take the derivative of each component, and then in the center mass frame, R equals 0 and R dot equals 0. So then the equations become R dot equals big M over M2 R1 dot, and then the same thing happens for just a regular R. And then the reduced mass is this. We can use the reduced mass in the equation, so we know that this is L and L1 and this is L2. So whenever we plug back in for the angular momentum up here, when we plug R back in and R dot back in for the first particle, then we get M over M2 R1 cross M1 M2 over M, over M times M over M2 R dot 1, and that just reduces to this M over M2, and this is the angular momentum we just said of particle 1. So then we could solve for L1, and it's just M2 over ML, which is what the book wanted us to do, but we also have to do it for particle 2. And particles 2, we could get this is the equation 8.9 as well. So then we have to solve for R. We have to take the derivative, and that would just be R, big R dot minus R2 dot. This is the only difference. It's a negative signs. And then in the center mass frame, R is equal to 0 and R dot is equal to 0, the big R. And then we get that R dot is equal to negative M over M1 R2 dot. And R is equal to negative M1 R2. And then we get the angular momentum is equal to M over M1 R2 cross M1 M2 M over negative M M1 R2 dot. And then it ends up being M over M1 R2 cross M2 R dot 2. And this is, like we said a while ago, the angular momentum of particle 2. So we get L2 is equal to M1 L over M, and we show that the momentum is conserved.